Good morning, everyone. Welcome to today's lecture. Today, we begin a new unit titled Absorption and Luminescence Spectroscopy. This unit is extremely important because it helps us understand one of the most fundamental processes in science: how light interacts with the matter. Spectroscopy allows us to study molecules without physically disturbing them by observing how molecules absorb and emit light. We can determine their structure, their energy levels, and their physical behavior. Throughout this unit, our focus will not only be equations but also physical understanding behind observations. So, this unit has two major parts. First, UV visible molecular absorption spectroscopy, and second is molecular luminescence spectroscopy. Let us begin with absorption spectroscopy. When light falls on a molecule, photons may transfer energy to electrons. As a result, electrons move from lower energy state to higher energy state. This process is called optical absorption. We will begin by studying the fundamental absorption mechanism. One mechanism is called free carrier absorption. This occurs mainly in semiconductors and conducting materials, where already mobile electrons absorb incoming radiation. This concept is very important for understanding optical materials and electronic devices. Next, we study transition between energy bands. Here, we distinguish between two types: direct transitions, where electrons move directly between bands without momentum change, and indirect transitions, where lattice vibrations called phonons assist the transition. Understanding this difference helps us interpret absorption spectra in solids. Later on, we will also introduce excitons. An exciton is a bound pair of an electron and a hole created after photon absorption. Exciton strongly influence optical properties, especially near absorption edges. Next, we will discuss Beer's law. Beer's law relates absorbance to concentration and path length. It is widely used for quantitative chemical analysis. However, and this is important, real experiments do not always follow it perfectly. We will analyze why deviations occur, including high concentration effects, molecular interactions, scattering, and instrumentation limitations. Understanding limitations is important as understanding the law itself. In the instrumentation part, that is after theory, we move toward laboratory instruments. We will study different light sources used in UV and visible spectroscopy. Then we compare single beam spectrometers and double beam spectrometers. Double beam systems improve accuracy by compensating for intensity fluctuations. In many experiments, molecules are dissolved in solvents. The surrounding environment changes molecular energy levels. This produces spectral shift. Two important shifts are bathochromic shift, where movement toward longer wavelength, and hypsochromic shift, movement toward shorter wavelength. We will learn how solvent polarity affect this shift. We will also learn how to identify transitions such as sigma to sigma star, pi to pi star, and n to pi star transitions. These assignments allow us to connect spectra directly with molecular structure. Now we move to the second major part, that is luminescence spectroscopy. Unlike absorption, luminescence involves emission of light after excitation. There are three stages occur in between, that is excitation, relaxation and emission. We will analyze two important emission processes. First one is fluorescence, a fast emission process, and second one is phosphorescence, a slower emission process. Involving spin forbidden transitions, using energy level diagrams, we will understand singlet and triplet states and intersystem crossing. We then define quantum efficiency, also called quantum yield. It measures how efficiently absorbed energy is converted into emitted light. This parameter is crucial for evaluating luminescent materials. We will study instruments such as fluorometers and spectrofluorometers. A major focus will be lifetime measurements. By analyzing decay curves, we determine radiative and non-radiative lifetimes. These techniques are widely used in material science and optical devices and biological imaging. To understand these units deeply, you should consult standard textbooks. This primary reference is Fundamentals of Molecular Spectroscopy by C.N. Banwell, which provides strong theoretical foundations. You may also refer to Molecular Structure and Spectroscopy by G. Aruldas. For additional conceptual clarity, for applied spectroscopy, consult Introduction to Spectroscopy. For instrumentations, use Principle of Instrumentation Analysis. For luminescence in solids, refers to solid state luminescence and luminescence of solids. Please ensure access to this text as we proceed through the course. By the end of this unit, you will be able to interpret spectra, understand electronic transitions, analyze spectroscopy instruments and evaluate luminescence process quantitatively. In the next lecture, we will begin with physics of optical absorption and mechanism. Thank you. See you in the next class.